Hey guys, so in the previous video we were talking about the redox equations. We saw that the oxidation number obviously changes in a redox reaction. It could be an element increasing the oxidation number, it could be decreasing it. So if it's a decrease in oxidation number, it's a reduction, and if it's an increase in oxidation number, it's an oxidation. If there's no change in oxidation number, essentially, it's not a redox in the first place. We saw that when it's a combined equation, one of the element is decreasing the oxidation number, and that is the reduction, and the other element obviously has to increase its oxidation number, so that element is suffering through oxidation. So one of them decreases it, the other increases it, and we looked at few examples. In today's video, we're going to be talking about a concept of redox equation, which is the displacement reactions. Now, a displacement reaction means that there is a compound, for example, it's a compound between X and Y, and another element, let's suppose B comes in, and B is, for example, like B wants to make a compound, and B says that I'm going to be taking the spot of one of these elements. Now, depending on what kind of charge B makes, B takes the spot of, let's suppose, X. So it forms a compound of By. Y is still over there, but now the X is a totally separate element. So this is a kind of reaction in which an element, it was an element in the beginning, makes a compound, and another element is released. So an element is making a compound. Displacement reaction is of two types basically. It could be a metal displacement or it could be a halogen displacement. So it can be a metal displacement reaction or it could be a halogen displacement reaction. Halogen displacement is essentially the non-metal displacement. So it is actually a non-metal displacement, by the way. In today's video, we're going to be talking about the halogen displacement, because that is a simpler one. In halogen displacement, when we talk about the idea, we know that halogen belongs to group 7. So we're going to be talking about halogen displacement. So halogens belong to group 7. These are group 7 elements. To make a compound, they tend to gain one electron. They tend to gain one electron and they become a -1 charge. They become a -1 charge. So what happens is that these are the 4 halogens that we should be worried about: fluorine, chlorine, bromine, and iodine. The 5th one is obviously acetylene, but we don't have to worry about it because it seldom comes in the exam. All of these halogens tend to gain electrons. They want to make compounds by reacting with the metals, and they want to make negative charges. So fluorine wants to make a fluoride after gain of an electron. Chlorine gains electron to become a chloride. Bromine wants to gain an electron to become a bromide. And iodine wants to gain an electron to become an iodide. These are the 4 essential halides that we can see forming within the case of halogens. Now obviously I'm talking about 2 atoms. Fluorine, chlorine, bromine, iodine are diatomic, so they all gain 2 electrons each, and they give you ions, which are obviously 2 ions because of the balancing of the equation. Fluorine is the most reactive of all of these. So fluorine is the most reactive one, and it gains the electron really easily. Fluorine making a negative charge is very easy reaction. Fluorine reduces itself very easily. But iodine is the least reactive. So iodine technically never gains an electron. And what happens is that one of the reactive halogens will gain the electron and the unreactive one will obviously lose it. So let's see what happens over here. For example, it's a halogen obviously with a metal. For example, let's say potassium is over here. Another halogen comes in. For example, another halogen is Y. In the case of this reaction, since halogen has a charge of -1. Halogen has obviously a charge of -1, but the other halogen has no charge on it, so it is a 0. By the end of the reaction, what happens is that potassium stays the same, but instead of making a compound with X, now it's a compound with Y, and the X separates itself. So previously it was a minus charge on the X, but now it's a minus charge on the Y. The X was the more, you can simply say the X was one of the halogens which was less reactive halogens, and Y was more reactive. So Y wanted to make a negative charge more easily, and potassium wanted to make a compound with Y. So potassium made a compound with Y, and ultimately what happened is that X was, in the beginning it was a -1, but by the end of the reaction it became a simple 0. So X has changed its oxidation number from a -1 to a 0, and that is oxidation. It's an increase in oxidation number. It's an increase in oxidation number. What about the Y? Y is actually a decrease in oxidation number. So Y has technically decreased the oxidation number starting from a 0 to a -1, and that is essentially a reduction, because that's a decrease in oxidation number over here. Let's try out an example. For example, we had potassium chloride and fluorine comes in. Since fluorine is more reactive, what will happen? Fluorine will make the negative charge more easily to make a compound. Potassium would be like, I want to be with fluorine because fluorine is more reactive, so it makes potassium fluoride and it separates the chlorine. You never write a single Cl, so you make a double out of it because it's a diatomic molecule. So previously it was a negative charge on the chloride because it was with potassium, and fluorine was a 0 because fluorine was essentially an element, it was pure element. But by the end, fluorine gets a negative charge making it a fluoride, and chlorine becomes a 0. So moving this equation a little downwards over here, essentially the chloride had turned itself from a -1 to a 0, and that is known as oxidation. So it's an increase in oxidation number. Chloride becomes a single chlorine, so it's an increase in oxidation number, increase in oxidation number. What about the fluorine? It changed its oxidation number from a 0 to a -1, and that is obviously a decrease in oxidation number, so this is gonna be a reduction. Decrease in oxidation number. Fluorine must have gained electrons because obviously this is what reduction is all about, and chlorine must have lost those, so it must have lost electrons. So the reactive halogen, which is normally the fluorine, gains electron. It gains electron really easily and becomes a negative charge. Iodine never gains electrons, so it tends to lose electron, but it's very seldom gaining the electron. Let's try out one more example and let's see what's going on over here. For example, let's change the name of the salt. For example, this case we have, let's say, sodium bromide, and I put in chlorine in front of it. So what happens over here is that chlorine is more reactive, so sodium makes a compound with chlorine instead, and it makes sodium chloride, where chlorine is the negative charge, because the more reactive halogen wants to be the negative, and since it already made a compound, the bromine has to be sacrificed. It becomes a simple bromine. When bromine was in the compound, it was a simple -1, but when bromine is alone, we know what alone elements are, they are 0. When chlorine was alone, it was a 0, but by the end, when it's in a compound, it's a -1. So technically bromine changes from a -1 to a 0, so it lost the electron So it is an oxidation, it's an increase in oxidation number. It's an oxidation for bromide. And in case of chlorine, it's changing from a 0 to a -1. So it's from a 0 to a -1. If we look at the ionic equation, we can write the ionic equation in this case. It becomes like this. So you cancel out the common charges, which is sodium, because it was +1 in both cases. You cancel them out, and what you get is a bromide with a minus charge, a chlorine with a 0, giving you a chloride with a minus charge and a bromine with a 0. So previously bromide was negative and chlorine was 0, and after the end of the reaction chloride becomes negative, bromine becomes 0. So here bromide is oxidized, lost the electron, and chlorine is reduced because it becomes more negative, it gains electron. The non-metal, the halogen, which is the reactive halogen, fluorine and chlorine, normally they react and they gain electrons more easily, they become more negative. Bromine and iodine, they often lose in the races, they become separate elements. Sodium, potassium, magnesium, don't want to keep them. So bromine and iodine is often released as a product, as a separate entity, they become a 0. So let's talk about one more equation, and this time we'll also talk about the observation. So what happens, let's suppose we are talking about an equation with, let's suppose magnesium, let's suppose iodide is reacting with bromine. What happens is that bromine in the beginning is obviously a 0 because bromine is the element over here. Magnesium iodide is a compound. Magnesium has a charge of +2. Iodide is a -1, and there are 2 iodines over here, so basically it's a -2 at all. Bromine is a 0 over here. By the end of the equation, what happens is magnesium makes a compound with the bromide because bromine is more reactive compared to the iodine, and ultimately the iodine is separated. So it becomes, magnesium is still a +2, but this time the minus is bromide and iodine becomes a 0. So technically magnesium doesn't do anything. So we don't have to worry about the magnesium. All we have to worry about is the fact that there were iodide ions in the beginning and there was a single bromine. It was a 0 over here. By the end, the bromide becomes the negative and the iodine becomes a 0 over here. So this reaction is all about iodide oxidizing itself from a minus to a 0. So it's an oxidation of the iodide atoms. Iodide oxidized over here because it lost the electron. The oxidation number increases. That is all the oxidation is all about. Bromine reduced because it must have gained electrons, and that is why its oxidation number must have reduced or decreased. So this is the reduction process, and the other one in the case of iodide is the oxidation process. What is the observation over here? The observation here is that iodine appears, which is black in color. So you can say black solid of iodine appears because that iodine is going to be black in color. So it appears black in color, so you see black color of iodine. In the previous equation, when you were receiving bromine, bromine is actually red-brown in color. So what you were getting red-brown color appears because of the bromine. In the other equation, when you were getting chlorine over here, chlorine is a pale green gas, so you would be getting pale green color appears. So whenever chlorine is a product, pale green gas appears. Whenever bromine is a product, orange brown color appears. Whenever iodine is a product, black solid appears. Or you can also say that violet vapors of iodine appear because iodine has violet vapors as well. So you can say violet vapors of iodine appear. But at the end of the day, you have to worry about the idea that the more reactive halogen will become negative. So fluorine will become negative over here, always the negative one, and iodine never becomes a negative very easily. Bromine never becomes a negative very easily. So this is about the halogen displacement reactions. So let's catch up with metal displacement in the next video.